Hello everyone, welcome back to my channel. I'm Vishit Ramesh and today in this video I'm going to be discussing about a concept in automata theory and compiler design. So today I'm going to be talking about the conversion of NFA to DFA. So why is the conversion of NFA to DFA required? NFA, also called as a non-deterministic finite automaton, can have a transition that goes to any number of states for a given input and state. A computer program needs precisely one transition for a given input from a given state. The process of converting NFA to DFA eliminates this ambiguity and allows a program to have a simpler compiler construction. NFA also suffers from combinatorial explosion. Reducing to a DFA can reduce states and transitions. So the steps for converting NFA to DFA. The NFA can have a 0, 1 or more than one move from a given state on a given input symbol. An NFA can also have null moves. On the other hand, DFA has one and only one move from a given state on a given input symbol. So the steps. Step 1. We convert the given NFA to its equivalent transition table. For each state in the NFA and each input symbol, determine the set of states reached by following the transition rules. Construct a table with rows representing states, columns representing input symbols, and the cells containing the set of states reached. Step 2. We create the DFA start state. The DFA start state is a set of all possible starting states in the NFA. This set is called the epsilon closure of the NFA start state. The epsilon closure is a set of all states that can be reached in the start state by the following epsilon transitions. Step 3. We create the DFA transition table. Instead of the individual states, the rows and columns represent set of states. For each input symbol, the corresponding cell in the transition table contains the epsilon closure of the set of states obtained by following the transition rules in the NFA's transition table. Step 4. We create the DFA's final states. The DFA's final states are the set of states that contain at least one final state from the NFA. Step 5. We simplify the DFA. We remove the unreachable states, remove the dead states, merge equivalent states. Step 6. We repeat steps 3 to 5 until no further simplification is possible. The final DFA obtained is a minimized DFA equivalent to the given NFA. Now let's take a look at the example. We need to convert the following graph from NFA to DFA. On accepting an input string, the Q0 stays. On accepting A, it stays in the Q0 state. On accepting B, it stays in the Q0 state or it moves into the Q1 state. Q1 on accepting B moves into the Q2 state, which is the final state. So the solution. So we first create the transition table. It consists of the states and the string A and B. The Q0 on accepting A stays in the Q0 state. Q0 on accepting B stays either in the Q0 state or moves into the Q1 state. Q1 on accepting A is a null state as there is no outgoing states from Q1 on A. Q1 on accepting B moves into the final state Q2. Q2 on accepting both A and B is a null state as there are no more outgoing states from Q2. So now let's consider the state Q0. Epsilon closure of Q0 comma A is Q0 from the table. Epsilon closure of Q0 comma B is equal to Q0 comma Q1. Q0 comma B is Q0 comma Q1. Now we consider the state Q1. Epsilon closure of Q1 comma A is a null state. Q1 comma A is a null state. Epsilon closure of Q1 comma B is equal to Q2. Q1 comma B is equal to Q2. Consider the states Q2. Epsilon closure of Q2 comma A and Q2 comma B both are null states from the table. Q2 comma A is null. Q2 comma B is also null. So the step 4. We consider the state Q1 Q0 comma Q1. So the epsilon closure of Q0 comma Q1 comma A is equal to epsilon closure of Q0 comma A union of epsilon closure of Q1 comma A. Q0 comma A is Q0 and Q1 comma A is the null state. So the union of Q0 comma null is equal to Q0. Epsilon closure of Q0 comma Q1 comma B is equal to epsilon closure of Q0 comma B union of epsilon closure of Q1 comma B. Q0 comma B is Q0 comma Q1 and Q1 comma B is Q2. So the union of Q0 comma Q1 and Q2 is Q0 comma Q1 comma Q2, which is a new state. So we need to consider the state Q0 comma Q1 comma Q2. So the epsilon closure of Q0 comma Q1 comma Q2 comma A is equal to epsilon closure of Q0 comma A union of epsilon closure of Q1 comma A union of epsilon closure of Q2 comma A. Q0 comma A is Q0. Q1 comma A is null. Q2 comma A is also null. So the union of these three is equal to Q0. So the epsilon closure of Q0 comma Q1 comma Q2 comma B is equal to epsilon closure of Q0 comma B union of epsilon closure of Q1 comma B union of epsilon closure of Q2 comma B. Q0 comma B is Q0 comma Q1, Q1 of B is Q2, and Q2 of B is null. So the union of these three is equal to Q0 comma Q1 comma Q2. So then we create the DFA's final states. So the states Q0 on A is Q0, Q0 on B is Q0 comma Q1, Q1 on A is null, Q1 on B is Q2, Q2 on A is null, and Q2 on B is null. Q0 comma Q1 on A is Q0, Q0 comma Q1 on B is Q0 comma Q1 comma Q2. Q0 comma Q1 comma Q2 on A is Q0, and then on B it is Q0 comma Q1 comma Q2. So the final DFA obtained, which is equivalent to the given NFA in the question, is as follows. So now let's analyze this figure. So Q0 on A stays in the Q0 state, so it's a self loop. Q0 on B moves to the Q0 comma Q1 state. Q0 on B moves to the Q0 comma Q1 state. Q1 on A is null, so there is no outgoing state from Q1 on A, and Q1 on B moves to the Q2 state, which is the final state. Q2 on both A and B is null, so there is no outgoing states on A and B from Q2. Q0 comma Q1 on A moves to the Q0 state. Q0 comma Q1 on B moves to the Q0 comma Q1 comma Q2 state. Q0 comma Q1 comma Q2 on A goes to the Q0 state. Q0 comma Q1 comma Q2 on B acts as a self loop on Q0 comma Q1 comma Q2, which is also a final state. So this figure is the final representation of the DFA obtained. Thank you everyone for watching this video. I hope you like and share this video. Thank you.